This is part 2 of a discussion of the identity principle, which says if you have two holomorphic functions on a region and they happen to agree on a sequence that converges to something in the region, that's enough to tell you that the two functions agree everywhere in the region, which is ridiculously powerful. And the strategy is we've defined two sets. These two sets are clearly disjoint. X is not empty. G is a region, which means it's connected. So you have disjoint sets that union together to give you the entire region, which is what I'm about to finish proving. I haven't proved it yet. And that means that one of them has to be empty by connectedness. If they both weren't empty, then G couldn't be connected. So one of these will have to be empty. X is not empty, so therefore Y has to be empty, and that means G has to be all of X. But X is the place where everything is equal to 0, which means that our auxiliary function here will be 0 everywhere. And so all I need to do is prove that for every point B and G, it belongs to one of these two. If H of B is not equal to 0, we're done. We already did that. So now we're going to split this into two cases. So we have H of B equals 0. And that's going to split into two natural cases according to the classification of zeros. The classification of zeros says either H of Z equals 0 in some region, some neighborhood around B. Right? That's one type of zeros. It could be 0 everywhere around B. Well, if that's the case, we're clearly in X. Here we're in Y. Here we're in X. Because that's the definition of X. There's a neighborhood around it where everything equals 0. The other case is that you might have H of B equals X minus B. Wait, did I get that right? Let me think just about this for just 1 second. Yeah. To the M times, how about Z minus B to the M? H of Z equals Z minus B to the M times B of Z for some holomorphic Z. They use G in the textbook. So this is the other option if you get a 0 there. But this is holomorphic. That means it's continuous, which means we can apply the same argument. If here's phi of B, that means there's some epsilon ball around it. It's holomorphic, so it's continuous. So there has to be some sort of delta ball that maps into this epsilon ball, and we can choose the epsilon so it avoids 0. So H of Z is not equal to 0 if Z belongs to the delta ball around B and Z not equal to B, which means that B belongs to Y. Which means we're done. So what have we done here, right? We know that f of zk equals g of zk. We want to prove that that means f of z equals g of z for everything in G. So I'm going to let h equal f minus g, which is holomorphic, and I need to show that it always equals 0. Well, I'm going to define two sets. All the sets, all the elements that have some neighborhood around it where h of z equals 0 everywhere in there. And we also need the set that all the b's such that there's a neighborhood around it such that h of z is not equal to 0 for any b, for any z in a neighborhood around b, except maybe at b. Okay, so these are clearly disjoint. You can show through essentially three cases that everything in G has to belong to one of them. Either it equals 0, it doesn't equal 0, or it does. And if it does equal 0, there are two cases. Either you're in X automatically, or with a little bit of continuity argument, you're in Y. So everything falls into these two. So G is equal to the union of these two, and these are disjoint. G is connected, so that means that one of these has to be empty. Oh, but W has to be an X. Why? Because if you draw any neighborhood around W, there are these ZKs that are converging. Remember these ZKs that are converging to W, which means that H of ZK equals F of ZK minus G of ZK equals 0. So there has to be a point that equals 0. So that means that it can't be in Y, so it has to be in X. So X is not empty. So G has to be all of X, and X has to be G, where it equals 0.